Hello and welcome back to the Calculus 1 playlist. In today's video, we're going to be talking about inverse trig functions. So we're going to continue our discussion with regular just inverse functions and how we can apply that to trigonometric, the typical trigonometric functions, that is sine x, cos x, and tan x. And we'll go over an extensive amount of examples. So without further ado, let's begin. So recall, we said a function can have an inverse if it is known as a one-to-one function. And from the last video, we said that we could determine whether a function is one-to-one using the horizontal line test. So the horizontal line test says that if we're able to pass through any point of the function with a horizontal line and it only passes through one and only once, then we have a one-to-one function, meaning that the function has an inverse. So let's look at sine, cos, and tan over these specific intervals. So for sine, we can see that we pass through with the horizontal line twice. So this fails the horizontal line test. Similarly, cos fails the horizontal line test. And tan also fails the horizontal line test. But this is strange. We know that we have the inverse functions such as arcsine and arccos as well as arctan. So how do we derive these functions? Well, let's say we restrict the domain of these functions. Then we are able to derive one-to-one functions within these specific domains, and we're able to do this for the function. So we'll handle this one by one. Let's start with sine of x. And I'll make two graphs. So let's say we restrict sine of x to a domain of kind of as such. So we go from negative pi over 2 to pi over 2, and we know the range will be from 1 to negative 1. And the graph of sine kind of looks like this. Oops, let's make that better. It needs to go all the way up to 1. Not the best graph, but you get the point that this is part of the portion of the sine wave. So we have this is 0. We have this coming like that. Let's make a bit better, just so it can be more accurate. So this is sine of x. F of x is equal to sine of x. And you can see that for every point, this passes the horizontal line test within this domain. Great, so this function has an inverse, and the inverse is known as arcsine of x, or sine inverse of x. And we know that it is reflected, the inverse function is the reflected function across the line y is equal to x. So if we do that, then we can say getting the inverse, so then this is the y-axis and this is the x-axis, y and x. Then over here we have these values, negative 1 and 1, and we have pi over 2, negative pi over 2. Then we have the function can be drawn as such, a reflection of the original across y is equal to x. This is f of x is equal to sine inverse of x. Great. So let's talk about the domain and range of this functions real quick. So the domain, we'd have to say, is for the original function is between negative pi over 2 to pi over 2. And the range is between negative 1 and 1. However, for the inverse function, we know that this is exactly the opposite. The domain is between negative 1 and 1, and the range is between negative pi over 2 and pi over 2. So we have just introduced a one-to-one version of the sine of x wave, sine of x function, and it is one-to-one. It has an inverse within this specified domain. Great, so let's look at cos of x. And I'll draw two graphs again. And for cos of x, I'm going to restrict the domain from 0 to pi. And you'll see why. So if we do this, and we have, this is the value of 1, this is the value of -1, this is our graph. This value right here is at pi over 2. So this is our function of cos of x within the specified domain of, I'll write the domain between 0 and pi, and range of -1 to 1. Great, we can see that this passes the horizontal line test. So this is also a one-to-one function. Great. It has an inverse. So I'll put the axis coordinates. So we have an arc cos of x, or a cos inverse of x. And this is f of x is equal to cos of x. So we know that in this case, the inverse of the function, again, is just the function reflected about the line y is equal to x. So we have -1 to 1. This goes from 0. It's pi over 2 is here. And this is pi. And then we can put this here. We have this here. And then if we go ahead and attach our lines properly, we have f of x is equal to arc cos of x. Perfect. This is exactly what we were looking for. And the domain and range of this function is just flipped from the original function due to the properties of an inverse. Perfect. So let's look at tan of x. And I'll draw two graphs one more time. So tan of x, if you recall what the graph looks like, we have two vertical asymptotes. This is at negative pi over 2. It's at pi over 2. We have vertical asymptotes at all multiples of pi over 2, integer multiples of pi over 2. And the graph itself looks like this. So f of x is equal to tan of x, 0. And so if we talk about the domain, well, the domain of this function, such that it is 1 to 1, as you can see, this function is 1 to 1 as well. Well, the domain to get a function of tan of x that is 1 to 1 is anything between negative pi over 2 and pi over 2, not inclusive, since these are vertical asymptotes. And the range, it actually goes from negative infinity to infinity. Great. So how does this look on the inverse now that we're aware that it is a one-to-one function under this domain? So for arc tan of x, or cos tan inverse of x. We now have these horizontal asymptotes, and they occur at negative pi over 2 on the y-axis and pi over 2 on the x-axis, or on the top of the y-axis, as well as we have this function that looks as such. Perfect. So we'll call this f of x is equal to arc tan of x. And the domain and range, again, once again, are just flipped. So the domain goes from negative infinity to infinity, as we can see, and the range goes from negative pi over 2 to pi over 2, non-inclusive. Perfect. So again, we kind of went over the how to derive a one-to-one function version of our trigonometric functions, sine, cos, and tan, and that would just be done by restricting our domains. So let's write down some formal definitions for them, and then we can go ahead with the examples. So sine of x, its inverse is sine inverse of x, or arc sine of x, with a domain, I'll just put short for d, of negative pi over 2 to pi over 2, inclusive. Cos of x has an inverse, cos inverse of x, arc cos of x, with its domain being between 0 and pi. Last but not least, we have tan of x going to tan inverse of x, or arc tan of x, with its domain being restricted to negative infinity to infinity. Perfect. So let's look at some examples. And before then, what if we're given some values of x outside this domain? So let's say we're trying to find sine of x, and x is not within negative pi over 2 or pi over 2. Well, it turns out a really good property about angles is that they're coterminal. Coterminal, sorry. So we can find the corresponding angles within our domain. So we're able to transfer these angles that were given and then transfer them to their equivalent value within domain. So angles are coterminal. And you'll see what I mean through some examples. So let's go through the first example. So say we have sine inverse of sine of 11 pi over 5. And we want to simplify this. Well, what does this equal? Well, first we know that the domain for our x value needs to be between negative pi over 2 to pi over 2 for sine. Well, we know that 11 pi over 5 is not within this domain. So what can we do? Well, let's subtract 2 pi, because we know that if we subtract 2 pi, we're just going back to the original point, right? So like, let's say I have on this graph, this right here is pi over 3. Well, pi over 3 is equivalent to pi over 3 plus 2 pi, because that would just be, see, if this is pi over 3, that would be pi over 3 plus 2 pi. So we can then subtract 2 pi from 11 pi over 5 to try and get it within our domain. So 11 pi over 5 minus 2 pi. Then we have 11 pi over 5 is equal to, or that minus, this becomes 10 pi over 5, and this is all equal to pi over 5. Great. So we can then say sine of 11 pi over 5 is actually just equivalent to sine of pi over 5. Well, now that we know this, we can go use this in our domain. Sine inverse of sine pi over 5. What does this equal now? Well, it turns out, since we have this in our domain, we can use the cancellation formulas to get what pi over 5 is. Recall, a cancellation formula is equal to x. Then we can say that sine inverse of sine pi over 5 is actually just equal to pi over 5. And that is our solution in exact form. Great, so we had to remember the concept of our cancellation formula, and that's going to come in handy a lot while we do these examples. Great, let's move on to the next example. So for this example, again, we're going to stick with sine inverse of sine 5 pi over 8. And we want to find out what this is equivalent to. Great, so we know that the domain for sine inverse is, once again, negative pi over 2 to pi over, negative pi over 2, not pi over pi, to pi over 2. Great. So where on the unit circle is 5 pi over 8? So we know that it's not within our domain of negative pi over 2 to pi over 2, but we can see that 5 pi over 8 is actually here. This is 5 pi over 8, 5 pi over 8. Now, we need to find a value that is within this domain, but gives us the equivalent expression of sine 5 pi over 8. Well, it turns out that if we have, if we're looking at sine, the values where sine is positive are in quadrant 1 and quadrant 2. So if we use the reference angle from quadrant 2, then we'll have the equivalent expression for the quadrant 1 value of sine 5 pi over 8. So if we go pi minus 5 pi over 8, that's to get this value. Well, that is just equal to 8 pi over 8 minus 5 pi over 8, which is equal to 3 pi over 8. And 3 pi over 8 is in our domain. 3 pi over 8 is somewhere here. This is 3 pi over 8, and it's in our domain. Great. So we know that sine of 5 pi over 8 is equal to sine of 3 pi over 8. And we can say that sine inverse of sine 3 pi over 8 as such. And we know then, using the cancellation formulas, that that is equal to 3 pi over 8. And that is our solution. Perfect, not so bad. We just had to realize quickly, okay, now that we're in the second quadrant and we're not able to add or subtract 2 pi to get within our domain, but if we look carefully, that we can see we can find the equivalent expression for sine 5 pi over 8 in quadrant 1. So doing that, we can solve our problem. Great. Let's move on to the next example. So in this example, we're going to have cos inverse of cos negative pi over 11. Great. So we know the domain of cos is between 0 and pi. So that's the domain for cos. Well, a cool property, I'm starring this because it's important. That's not how you spell property. Property of cos of x is that it's an even function. And if you recall, we can define an even function as a function that can be written as such. So we can say that cos of negative x is equal to cos of x. Well, I guess I'll flip it for notation's sake, but you get the point here. That we can say that since we can do this, we can say that cos of negative pi over 11 is equal to cos of pi over 11. And this is within our domain. So now we can go cos inverse of cos pi over 11. And this is all equal to pi over 11 using our cancellation formulas. Great. So it's just important to remember these little key tricks when trying to solve these problems. Let's go on to the next example. So the next example, we have arc cos of x. Oh, sorry, not of x. We have arc cos of cos 13 pi over 4. Okay, so again, we know that the domain of cos inverse is between 0 to pi. So let's think about this. For 13 pi over 4, we need to restrict this to be a part of our domain. So what we can do is first subtract negative 2 pi. Well, 13 pi over 4 minus, and this becomes 6 pi over 4 is equal to 7 pi all over 4. Great. Let's draw this pi closer. Great, so let's draw this out on the unit circle to see kind of where we're at. And so 7 pi over 4 is over here. Now, we need to have an equivalent value of 7 pi over 4 for cos that is within the domain. So let's write down the cast real quickly, just for a reminder. And our domain for cos is between 0 and pi. So since we're not able to subtract 2 pi and get a value within our domain, what we can do is find the equivalent expression of cos. And it turns out cos is positive in this quadrant, positive in this quadrant. So our value will be in the first quadrant. It will be right here, and this would be pi over 4. Great, so we can say cos of 7 pi over 4 is equal to cos of pi over 4. Because of this, we can say that cos inverse, or also our cos pi over 4. And we know that using the cancellation formulas, once again, this is equal to pi over 4. Great. So for the next example, it's going to look complex. I saw this while I was studying this topic, and it looked very interesting. Tan inverse of sine of cos inverse of cos at 3 pi over 2. And it looks scary at first, but I promise you it's not that bad. First, let's find out where we are on the unit circle. So we're at 3 pi over 2. Well, it turns out 3 pi over 2 is right here. This is 3 pi over 2. Well, if we're at 3 pi over 2, we know that cos is 0 at this point. So cos of 3 pi over 2 is equal to 0. Great, so we have tan inverse of sine of cos inverse of 0. So that gets rid of that problem. So cos inverse of 0, we know that cos within our domain of cos, because remember, domain of cos is between 0 and pi, the only place where we get 0 during this domain is at pi over 2. So we'll get tan inverse of sine at pi over 2, since this is pi over 2. Great. Well, what is sine at pi over 2? We know that sine at pi over 2 is equivalent to 1. So then we have tan inverse of 1. And the only place within the domain where tan is equal to 1, there's only one point where we have tan tan output at 1 is pi over 4, because that is the point where cos and sine are the same. So that's actually not that bad. It looks a little bit scary, but breaking it down, we can solve it very straightforward. So the next example. So this example, again, it's going to look a little bit complex, but I promise it's not that bad. Cos of tan inverse of 14 pi over 3. Great, so let's write down the domain of cos and tan quickly. So we know that cos, the domain, is between 0 to pi, and for tan, the domain is negative infinity to infinity. Well, hold on a second. There's no restrictions on the domain for tan inverse, right? So since there's no restrictions on this domain, we can say that using the cancellation functions that tan of tan inverse of 14 pi over 3 is just equal to 14 pi over 3. So that completely gets rid of that part of the problem. So now we have cos inverse of cos of 14 pi over 3. Great, so now it just comes back to doing the exact same thing. Let's subtract 2 pi from 14 pi over 3. 14 pi over 3 minus 2 pi. Well, we get 14 pi over 3 minus 6 pi over 3. That leaves us with 8 pi over 3. And we can subtract 2 pi again, minus, that's equivalent to 6 pi over 3. We get 2 pi over 3. Is 2 pi over 3 within our domain? Well, if we look, our domain for cos is 0 to 2 pi, is between 0 to pi, and 2 pi over 3 is within this domain. So we can say that cos inverse of 2 pi all over 3 is equal to 2 pi over 3. Very straightforward again. This next example, again, I saw this and I thought it was a very interesting example to look at. It's not too difficult. It might seem a little bit confusing, but let's work through it. So we have tan of sine inverse of 3 over 5 x. And let's simplify using your right triangle. So wait, what does that mean? Let's think about this. We need to describe what this function is talking about. So let's say we have, let's say that sine of this expression, sine of 3 over 5x. Let's say that's equal to, or the sine inverse, of 3 5 over x is equal to a. Then we can say sine of a is equal to 3x all over 5, right? But what is sine of a, 3x over 5 really look like on a triangle? So if we draw our right angle triangle, this being our right angle and this being our a value, well, we can then say that the hypotenuse is 5, the sine is 3x, and this value right here is just 25 minus 9x, right? From b squared is equal to c squared minus a squared. And you get b is equal to root c squared minus a squared. So 25 minus 9x all square rooted. Great. Well, now that we know that, what is tan of this value, tan of a? Well, we know that tan of a is just the opposite over the adjacent. So tan of a, right? And we said that a is equivalent to this expression, so that we can use tan of a. Tan of a is actually just equal to the opposite side, which is 3x, all over to root 25 minus 9x. Perfect, and that's our solution. It might seem a little bit trippy at first, but if you think through it, it's not that difficult at all. We just represented our angle, our tan angle with a, and we solved what it would look like using x and a right triangle. Great. And for our last example, I have one more example. Again, it looks a little bit challenging, but it's really not. Sine inverse of sine of cos inverse of cos 75 pi all over 4. Great. We got one more on the outside. So how are we going to do this? Recall the domain of cos is domain of cos is 0 to pi, and the domain of sine is negative pi over 2 to pi over 2. So we need to find values within this domain. So start with 5 pi over 4. Let's subtract this by 18 pi to get back to the same spot. 18 pi is very close to that value, if I'm not mistaken. 5 pi over 4, 18 pi, that is equal to, that's 72 pi all over 4. And that gives us 3 pi over 4. Great. Well, 3 pi over 4 is in this domain of the cos between 0 to pi. So we can say sine inverse of sine of cos inverse of cos 3 pi all over 4. And this just gives us, for this inside function of cos inverse and cos, that is just equivalent to 3 pi over 4. Great. Now, what is the domain of sine again? The domain is between negative pi over 2 and pi over 2. So let's see where we are quickly on the unit circle. We're at 3 pi over 4, which is here, and we need values within this domain, which is negative pi over 2 and pi over 2. So the equivalent value of sine is going to be in the positive quadrant, since our value of sine is positive in quadrant number 2, right? So our equivalent value needs to be in quadrant number 1, and that is actually just this angle, which is pi over 4, right? Since sine of 3 pi over 4 is equal to sine of pi over 4, and you can verify that. Thus, we can say that sine inverse of sine of pi over 4 is just equal to pi over 4. And we'll box that. You should be good to go. Great. That's all the examples. So we went through an extensive amount of examples, just trying to prove that they may look a little bit difficult and they may look a little bit tricky, but they're able to be solved. There's just some key properties to remember. The property of cos of x is that it's an even function, and also remembering to subtract or add values of 2 pi to angles, because angles are coterminal, and that we're able to restrict the domains of sine, cos, and tan such that we're able to have inverse functions that are one-to-one. So great. If you enjoyed this video, please feel free to share, like, or subscribe, and I'll see you in the next video.